So thanks for coming by, fellas. And today we are going to introduce a new a new technique by attacking Windows by Windows. And my name is Li Zhou, and this is my colleague Ying Liang.
Hi, everybody.
Okay, we are both from the Tencent PC Manager. So this is an outline of today's presentation. First of all, we are going to introduce about ourselves, our teams, and then we are going to have a brief view of the old school styles to exploit the Windows kernel. And then we are going to talk about the Windows 10 limitations. And I'm going to introduce the 0 to 1 exploitation, and my colleague Ying, he will introduce the 1 to 0 exploitation. Okay, so first of all, Ying will introduce the team. Okay.
Hi, everyone. My name is Kai Debugger, and I'm one of the members in Tencent Synapse. First, I'll take a short time to introduce our team. We have 7 members. Xin is our team leader. Godze is analyzing Flash and PDF memory allocation. Kai is me, and I'm responsible for finding Windows kernel vulnerability and writing exploit. Michael is exploiting PDFs. Kevin and Via are doing fuzzy jobs. Rosma is doing AI combination to vulnerability exploitation. In part 1 2016, we got the system privilege by hacking Adobe Flash in only 3 seconds, and won the title Master of Palm by achieving the highest score with King Team. Also, we got the system privilege and achieved the prize in GeekPalm by hacking Surface Pro 4 in only 1 second. In 2016, we received 14.6 acknowledgements from Microsoft and Adobe. Today, we will show the techniques of Windows kernel exploit when we use in Part 1 and GeekPalm. Should we start?
Okay, so I'm going to introduce the first 0 to 1. So basically, if we want to exploit or if we want to attack the programs in user space or the programs in the kernel space, we have to deal with 3 problems, right? So the first one is where to write, the second one is what to write, and the third one is what can we do right now. So for the first question, I think everybody knows that we should interrupt the normal procedure of the process and force it to jump into our shell code. And then what to write, actually we want to make use of the abnormality and make use of them. And the third one is after we alter the data, what can we do to reach the final destination, like escalate the privileges to the system privilege or gain whatever we want. So in the old days, if we want to attack Windows XP or Windows 7, so these three questions are quite simple. So we need to focus on a structure that is called help dispatch table. We can call an API function that is anti-query system information to get the loading addresses of all the kernel modules. We add some offset, and we can finally get the help dispatch table. So this help dispatch table is a kind of a function distributor. There's a lot of function starting address in this help dispatch table. So what we need to do right now is to replace one or many of the starting address with our shellcode address in the user space. So then when we call the function anti-query interval profile, which has a kernel version of the anti-query internal profile, and the kernel version will find the address of the starting address in the help dispatch table, which now is our shellcode address in the user space, and execute our shellcode. So it is very easy for old school days. But I think the Microsoft security engineers are quite smart, right? So they create several of the protections to forbidden these actions. So I think there are 2 most effective ways. So the first one is the integrity verification, and the second one is SMEP. So for the integrity verification, the system will, we both know the process has many attributes, so the integrity is one of its attributes. So the Windows will check whether the process is a high integrity user or a low integrity user. If it is a low integrity user, when we call the function NT-Curie system information to get the loading base address of the kernel modules, then what we have right now is only a status access denied. So some of the hacking teams, they create some ways to do to bypass it because they found some of the information leaking vulnerabilities. So this information leaking vulnerabilities will give us the information about the loading address, but this is another vulnerability. So we have to use two vulnerability to gain our final to reach our final destination. The other protection is called SMEP, which refers to the supervisor mode execution protection. So basically, this protection will forbidden the CPU or the system to execute the code in the user space. So what if we just run the code? If we just do like the old school days, we replace the shellcode address to the address in the health dispatch table and execute it, then what we have right now is a blue screen right there. We got nothing from it. So some of the hacking teams are very smart, so they came up with the ideas of the ROP chain. I think everyone knows it, ROP chain. They use the ROP chain to remove the SMEP protection. But in order to do so, they also need a information leaking vulnerability to get the loading base address of the Win32K driver, and then use the ROP chain to close the protection. So basically, we need two vulnerabilities. We need the ROP chain, and we both know creating or constructing this kind of ROP chain is very difficult or very annoying. So everybody is upset. So this is going to be our new exploit method. So our method has many advantages. We can use it on all Windows operating system, no matter it is x86 or x64. We only need to trigger one time. We can bypass SMEP. We do not have to create any of the ROP chain. We just only change one bit in the kernel space, and we can bypass the KALSR. And now I'm going to introduce the details of it. So back to the three questions, where to write? Since Microsoft does not allow us to use the NT-Curie system information to get the loading address, but there's something that they did not find. So this is a G shared info structure. Actually, you can see the G shared info structure has a kernel is in the kernel space. But if you loading the user32.dll, the dynamic link library, so this kind of memory will be mapped into our user space automatically by the function view of section, map view of section by that function. So basically, the data in the G shared info are mapped into the user space. So this is a kind of information leaking vulnerability, but Microsoft did not regard it as a vulnerability. Maybe they will fix it in Windows 11, Windows 12, I don't know. So as you can see, the p-head is a member of the handle entry. So this p-head will point to a window object. Also, it can point to a menu object. So I'm going to focus on the window object. So basically, what we need to write is in the window object. So what's in the window object? There's a very, very important structure that is called tag window object. So window is a basic object in Windows. We always use create window API to create a window, and then in the kernel will create a tag window structure. So in this tag window structure, it has many important information like the parent window, like the window process, like the name of the window, like the window extra data. So what should we do right now? I think we should focus on the Windows extra data. let's look at the structure of the tag window. So you can see there's a member called CB window extra. What is CB window extra? CB window extra is actually the size of the window extra data section, as you can see at the bottom of this structure. So we could use two APIs to control the tag window structure. The first API is set window long, and the second one is get window long. But there's two params that it is strange. It's an index. What is an index? Actually, we can regard the window extra data section as an array, as a deword array. So basically, the n index is the index in the window extra data. So what we need to do, what we could do right now is to use set window long to write something in the window extra data. And we can also use get window long to read a word in the window extra data by using the n index param. So this is a case that is a normal case. So we can see that we have two windows, the window 1 and the window 2, and between them there are other objects. So in window 1, we have the CB window extra. The value is hex 8. As we can see, this is a binary formation of the CB window extra. In the position 3, there is a 1, and the others are both zeros. So what if we change the higher speed to 1? What if we do so? Yes, we just change the window extra size from a very tiny size to a very huge size. So in our case, the original size is 8, right? And now we change it to 2 gigabytes. So as you can see right there. So basically, the data just right behind the tag window of window 1 becomes our extra data. So we could use the set window long to modify the data, right? To modify the data, just regard this stuff as our data. So we can use that API to change it. What we can change it whatever we want. We can change the data into our future for our future exploitation. So how can we read from the kernel space? Okay, since now we have changed the window extra data size from 8 bytes to 2 gigabytes. So that means the window 2 is probably by modified to the extra data of window 1. So now let's focus on a member that is called string name. String name has 3 members: the length, the maximum length, and buffer. So this buffer actually contains the character of the window 2. But now we can change the data in the window 2, right? So basically we can set the buffer to the place we want to read. And then we call internal get window text to read whatever we want in the kernel space. Is that amazing? So the same, we can also write something to somewhere by using the API NT-user def set text. What we need to do right now is to set the buffer to the place we want to write, and then we call this API function, and our data are written to the position we assigned. So basically, we can call the set window long for many times. We can reset the buffer address for many times, and we can read and write anywhere we want. Okay, so now how to escalate our privilege from the normal user to the system user? Basically, we just do reverse engineering of the get window thread process ID, and we found a relationship between the tag window structure and the eProcess at the right, the eProcess structure. So as you can see, in the tag window structure, there's a member called PTI. The PTI points to a tag thread info structure, and tag thread info structure point to the K-thread structure. And at the offset 220, in K-stress structure, it points to, there's a member called process, and it points to the E-process structure. And in the E-process structure, there's our token. There's our token of our process. But the windows help us. Why? Because if we do not set our parent window to our window, Windows will force the desktop window as our parent window. So basically, we can use this spawned parent in our tag window to find the desktop window. And through the same procedure, we can finally reach the CSRSS.exe, the system process. And at the same offset, we can get the system token. What we need to do right now is to use these two API, set window and get window, to read the token from the system token. And then we write it to our token position. So this is going to be our escalation process. So this is a real case, the CVE 2016-0174. At first, we load a font into the kernel, and the kernel will create a PFF object. And then we free the PFF object, but actually in the kernel somewhere stores the reference of the PFF object. And then we immediately reallocate the same size of the memory, and this is definitely a use after free, right? And then we free the font again, and finally reach the step 5. Step 5 is a assembly code. Yeah, it's right there. So RAX, the register RAX, is actually controlled by us. We can let the RAX point to the at the tag window, the offset DF at the tag window, and then plus hex C, and we will reach at the highest bit of the CB window extra. And now what we need to do now is to execute the assembly code that is OR, DWOR, PTR, RAX, and plus hex C and 2. And we can change the size of the CB window extra from 0 to 2 6 zeros. So in the part 2, we are attacking the flash, and we are using the flash to execute any word in the edge, Windows Edge, and we escalate the edge's process, the privilege of the edge process to the system process privilege, and then we escaped from the sandbox. We completed this job in 3 seconds, and we won the 50,000 reward and the Surface Pro 4. So in other case, there are 2 assembly code right there. Yes, as you can see right there. Basically, what we need to do right now is to make the CB window extra as large as possible so that we can control all the data just right behind it. So if you get it, and you will make a success. So in summation, where to write? We need to write the CB window extra. So what to write? Actually, we just change 1 bit of the CB window extra and make it a very large size. So what can we do right now? After we did that stuff, we can read from anywhere, we can write any value to anywhere, and we can steal the token of the system process to our process. That is a whole procedure of our exploitation from 0 to 1. Okay, so now, and my colleague In will introduce another technique which refers to 1 to 0.
How to exploit Windows kernel by a tiny bit from 0 to 1? The previous presentation gave us the answer. Now we have a new question. If we can modify a bit from 1 to 0, how can we do the same job? Let's have a brief view of the function nt-gdr get font Unicode ranges. This function calls 5 other ones and return. At first, it calls GRE get font Unicode ranges. The first param HDC is the handle of our device context. Our font has been selected into the device context before. If we set the second param to be none, we will get the range size of the font only. Then the size is sent to allocate free temp buffer, and we will get a temp memory buffer. We call GRE get font equal ranges again, set the param to the memory buffer, so that the range data would be written to it. We deliver the data from caller to user space and freeze the temp buffer. 1, 2, 3, 4, 5 steps. It seems to be very simple. However, in system security, simple sometimes means, look, there's maybe a vulnerability. Let's consider a situation. We have two kinds of font. One got small ranges. Suppose its size is 1. The other got large ranges. Suppose its size is 10. And we have two threads, thread A and thread B. They are both doing infinite loop. Thread A calls ntgdi get font equal ranges, execute the 5 steps. Thread B do the same, do the selection job. It will select small and large font. We may have a process like this. Thread B selects the small ranges font into DC. Thread A calls GRE get font equal ranges for a function and get the small size 1. Then it allocates a memory buffer, which is only 1 byte. Then thread B selects the large ranges font into DC. Thread A call GRE get font equal ranges again with the 1 byte buffer. Now thread A will face the large range font. So 10 byte range data is going to be written to 1 byte buffer. What will happen? We will get an overflow. So this is the CVE 2016-3355. The whole process will randomly happen with 1 second when I test on my computer. My exploit procedure is like I said before. I create 2 fonts and load them into the system at first. Then I nudged 2 threads and let them do racing condition. After overflow happens, I could control the R15 register. Then with the help of this assembly code and the R15 register, I can modify 1 bit of anywhere, change it from 1 to 0, just like here, position 2. Now we have the overflow and R15, but how could we exploit? What about CB extra as we mentioned before? We could turn 4 to 0 or hex 14 to hex 10, but it seems to be useless because we still cannot modify the next target window structure. What about flag? There is a lot of flags in target window structure. We can turn some of the flag bit from 1 to 0, but I didn't find any appropriate exploit. Let's recall GCL info. In handle entry structure, the offset hex 10 is bit type. It shows us the type of object pointed by p head. If it is 6, the object is clip data. If it is hex C, the object is a monitor. If we take away the 4 from the 6 and turn it to 2, then we force the clip data object to the manual object. So we have a type confusion vulnerability. I can control the pointers in the manual object and modify other memory. It sounds good, and actually I wrote a whole process, whole exploit based on the technique before. However, this is not a general solution. What if we need to modify the position 0 or position 3? So I started to find out whether there is a more general exploit. The answer is the reference count. In each main 32K objects, there are like target wind, target manual, target monitor. There is a single object member at offset 8. It means the reference count of the object. If some other object refer it, then it's a reference count 81. In the caller, there are 2 functions which can be used to modify the lock object. One is HM assignment lock. It is used for increasing the reference count. The other function is HM assignment unlock. It is used for decreasing the reference count. If we call destroy window or destroy menu, The function HMark object destroy will be invoked. It will check whether the reference count is 0 or not. If it is not, the object will not be destroyed. If it is 0, the object will be freed. Let's have a look at another basic object in Windows, menu. We can call create menu API to create our menu. At the same time, the caller create a tag menu structure. We can call append menu API to append a menu onto another one. Right here, I create two menus, menu A and menu B, and call append menu for 4 times. The data structure in the caller is shown right here. At menu A, RG items point to your array, and the C items indicate the count of the members in the array. In our case, there are 4 tag items, and the SP submenu all refer to menu B. So the reference count of menu B is 4, which is right here in the syntax object. Since there is no other menu appending to menu B, we could say its signal items is 0, and RG items points to none. If we call destroy menu to destroy menu B, we will be failed because the syntax object of menu B is 4. The system refuses us to do so. With the help of overflow and R15 register, we can turn syntax object of menu B to be 0. What can we do now? So we can destroy menu B, freeze the memory of menu B. To be noticed that the SP submenu is still pointing to menu B, the freed object. After destroying menu B, we have to call NT-user deficit tags immediately to set a name for window. If the window has no name, then a memory would be allocated from desktop heap for storing the name string. What happened if the name string size is the same as menu B? The system will allocate the menu B memory for us, which we just destroyed. I can set the name string to be any data, so I can set the menu B's content to be any data. I can set the pointer of menu B to anywhere. Menu B turns to be freed memory, then turns to be a fake menu. So right now, SP submenu points to a fake menu. What we do now is to make a simple fake menu. We set the C items to 1 and let RG items point to a memory we controlled. In that memory, we fake a tag item structure and set the SP submenu member to a tag window with offset hex 80. In normal situation, SP submenu points to a tag menu structure. Now we force it point to a tag window structure in the middle. We regard it as a tag menu structure, which we refer to a virtual menu. What we care is CB window extra, which is also DW menu data in the virtual menu. Now let's put them together. We can set information of our menu by calling set menu info API. There are 2 marks which we are interested in. When we specify the mask MIM menu data, we will set the DW menu data of the tag menu. When we specify the mask MIM applied to submenus, we will also set the DW menu data of the submenu one after another. Let's look at the picture. We built a chain before. Menu A submenu used to be menu B. Now it becomes a fake menu which is controlled by us. The fake menu submenu is a virtual menu with point to a tag window structure in the middle. When we specify those 2 masks, we will finally set the virtual menu's DW menu data. That means we will finally set the CB window extra of window 1. We could escalate the privilege to system as we said before. To be noticed that the C items of the virtual menu is 0, so the operation of setting submenu's data will be stopped in virtual menu. The function ntgdi get function Unicode ranges is added in Windows 2000 SP2. It has been 15 years. Perhaps it's too simple, and so nobody noticed it. And Microsoft didn't change the code of the function. From Windows 2000 to Windows 1, from Windows 2000 to Windows 10, from 32-bit to 64-bit, the procedure remains the same. What they do is getting the size first and then allocating memory, then getting the data all the same. So this vulnerability exists in all the windows you can see. In the exploit I mentioned before, I used the window and the menu. Those are the basic objects in Windows. Unless you forbid Win32k driver, I can launch the attack and get the system privileged by any user. The offsets shown in the PowerPoint are within Windows 10, 15, 11, 64-bit. If you want to attack the other windows, you only need to adjust the offset. Now let's just rule them all. Let's take a summary. How to exploit Windows caller by a tiny bit from 1 to 0. The answer is writing 0 to target menu C lock object. So we create another use out-of-frame vulnerability, make a fake menu, and reset the CB window extra of a target window. I use the menu object for the job. You could pick another one if the object has pointers, and you can write data to the pointed address. That's all. Thank you for the coming. Any questions?